In this video, we will discuss how molecular orbital theory is used in organic chemistry. Our goals for today are to be able to draw an MO diagram for simple small molecules, where simple means containing just a few atoms, to rank the energies of molecular orbitals, such as sigma, non-bonding, pi, sigma star, and pi star orbitals, to draw cartoon molecular orbitals for sigma and pi symmetries, and finally, to explain the difference between a bonding and an anti-bonding orbital. Actually, let's add one more goal. We would like to be able to identify the frontier molecular orbitals for small molecules. Keywords for today. Yeah, MO, 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 MO. So clearly, we'll be talking about orbitals, and specifically molecular orbitals. Let's get started. We'll begin by drawing cartoon orbital diagrams that show spatial orientation and phasing for all of the orbitals that each of these atoms can use to make bonds. Please pause and try this exercise. A carbon atom with no hybridization has the valence shell orbitals of the 2s and then the 3 degenerate 2p orbitals. Those 2p orbitals differ in which axis they're oriented along. A carbon atom with sp hybridization, we imagine that the 2s and one of these 2p orbitals have been combined to make two hybrid orbitals. Notice that if you overlaid these hybrid orbitals, there would be a 180-degree angle between them. A carbon with sp hybridization will have linear geometry at that carbon. The two orbitals that were not combined to make the hybrid orbitals still remain, and these orbitals, the p orbitals, they can make pi bonds. Those pi bonds will be at a 90-degree angle from the plane containing the sp orbitals. For a carbon atom with sp2 hybridization, we imagine we've taken three orbitals, the 2s and two of the 2p's, combine them to make three new hybrid orbitals. If we overlaid those orbitals, they would be at a 120-degree angle from one another, all occupying the same plane. And here I'm ignoring the small lobes. Atoms with sp2 hybridization have trigonal planar electron geometry. Recall, hybridization explains geometry. The trigonal planar, sp2, linear, sp. Finishing up our discussion of the sp2 hybrid carbon atom, we see that there is one p orbital that was not used to make the hybrid orbitals. It remains. I refer to that as a leftover p orbital, and that p orbital can be used to make pi bonds. It will make a pi bond that is perpendicular to the plane occupied by the sp2 orbitals. It also might be empty. Finally, we can discuss a carbon atom with sp3 hybridization. That atom will have a tetrahedral electron pair geometry. The four sp3 orbitals result from combining all four of the atomic orbitals. Combine four, you make four. If we overlaid these four sp3 orbitals, they would be at 109.5-degree bond angles from one another, explaining that tetrahedral geometry for the carbon with four electron domains. Just as for the sp and sp2 hybridized carbons, the sp3 hybridized carbon, we imagine that it uses these hybrid orbitals to make sigma bonds or hold lone pairs, right? It's holding the electron domains as far apart as possible according to its VSEPR geometry with the hybrid orbitals. Now, of course, there are no leftover p orbitals for the sp3 hybrid carbon, right? It used them all to make the hybrid orbitals. So can an sp3 hybridized carbon make pi bonds? No, it cannot. It cannot make pi bonds because it does not have a p orbital. All right, if that is unfamiliar or you need a little bit of review, you can go back and view the valence bond theory and hybridization lesson. Now that we've reviewed, I have a question for you. Why does molecular hydrogen exist and not molecular helium? Write down your answer. What did you come up with? Okay, thank you for sharing. All right, let's think about what you already know that will help you answer this question. So what do you think you already know? Yeah, okay, so you know how to draw Lewis structures. You know valence bond theory. Valence bond theory. What do you think you need to know? I suspect I'd be asking you, why? How do you know? How do you know? So what do we need to know to fully answer this question? We need to know molecular orbital theory. Excellent, let's learn it. To introduce ourselves to molecular orbital theory or to refresh our memories, let's take one more pause. Please answer these questions. Humor me, especially these drawing pictures and giving examples parts. All right, go, do it. An atomic orbital is a region in space where an electron is allowed to exist and has a specific energy. What's a molecular orbital? Skip down to the next question. What is a molecular orbital? Yes, it is also a region in space where an electron is allowed to exist with a specific energy. So what are the differences between atomic orbitals and molecular orbitals? Right, atomic orbitals are regions of space around atoms. What are molecular orbitals? Regions of space around molecules. Yes. And we will mostly think about molecular orbitals right now being between two atoms, but actually, the truth time. Molecular orbitals, the real ones, are around the entire molecule. And they are pretty difficult to model, though chemists can do it. And that's why we just stick to thinking about molecular orbitals usually as being between two atoms. But even today, we'll see some examples where we actually have to consider more of the molecule. Now to your pictures. What examples of atomic orbitals did you give? Yeah, we can think about an s orbital, a p orbital, maybe even a hybrid orbital, an sp or sp2 or sp3. Let's do sp2. What examples of molecular orbitals could you draw? Because I got to tell you something. Atomic orbitals, as you learned from that last lesson, they are boring. We are talking about molecules, but unfortunately we needed to know atomic orbitals before we could think about molecular orbitals. Molecular orbitals are exciting. Did you draw any examples? All right, let's see how you did. We will revisit the Lewis structure for the simplest molecule, which is the hydrogen molecule. It's the simplest, and I don't mean easiest. It's actually not easy at all. When chemists try to model hydrogen by quantum mechanics, it takes a lot of work because there are 4 particles, right? It has 2 protons and 2 electrons. Turns out that's not easy to model when you have 4 different variables like that. So here's the simplest molecule. Again, I don't mean easy when I say simple. I just mean small and few parts. Can we describe the location and energy of the electrons in this molecule? Can we describe the electrons in that molecule at all? Well, sure we can, as we discussed in valence bond theory. And we would take the valence orbitals for these hydrogen atoms and bring them together in space. That would result in a new orbital, and it will have sigma symmetry, right? Sigma symmetry because there is cylindrical electron density around the bond axis. So can we describe the location of the electrons in the hydrogen molecule? Can we answer this question a little bit better now? Sure, we can say that the electrons have the highest probability of being where? Where do you think? Yes, between the 2 nuclei. That's why the line that we draw in the Lewis structure is between the 2 nuclei, because that is where the electrons are most likely to be. In between the 2 nuclei, The electron is attracted to both nuclei, right? It's attracted to both of them. Actually pulls them both towards itself. We'll talk about that in a little bit more in a bit. And of course, the alternative would be the electron is outside the nuclei. Excellent. What can we say about the energy of electrons in that sigma orbital? Well, the electrons will be lower energy than in the atomic orbital. Right? They're between two nuclei now rather than one. So that energy of attraction is going to go down, and they're lower energy. Yes, they're in a very happy place between two nuclei. Well, we've got this all figured out, right? We're done. No, we are not done. Valence bond theory meets the rules of quantum mechanics. So in valence bond theory, we just applied, we showed that the overlap of two atomic orbitals forms a single covalent bond. We did that right here. The overlap of two atomic orbitals forms a single covalent bond. However, the rules of quantum mechanics require that the number of orbitals must be conserved. You actually already know this. Recall hybridization. The slide's a bit messy now, but bear with me. So when two orbitals, the s and one of the p orbitals, combine to make hybrid orbitals, I told you that two orbitals must be made. The number of orbitals is conserved. So how does this relate to what we're talking about right now? Well, we've drawn two orbitals overlap, and how many orbitals did we show being formed? One. So we're missing something. There must be another orbital. Anybody know what it is? All right, good. So when two orbitals are combined, two new combinations must result. We will demonstrate this with the hydrogen molecule. We have already shown how the 1s orbitals come together in phase to generate a sigma molecular orbital. So these regions come together, they overlap, and they constructively interfere to make this new orbital. I drew out what I mean by constructive interference last time with these simplified wave functions. So we can imagine that we have two waves coming together. I'm going to add them up, and they're in phase. So when I add them, their positive amplitudes are going to add up, and then the negative amplitudes are going to add up. They're going to constructively interfere, and we're going to get a bigger wave. That is what is meant by adding two orbitals in phase. Remember, orbitals are modeled by wave functions. Now, there's another possibility, and we did not consider it so far. Instead of adding the orbitals in phase, what if we add them out of phase? The 1s orbital can be either shaded or unshaded. You can have either a positive amplitude or a negative amplitude if you're thinking about it as a wave. Because the orbitals have different phases, destructive interference is observed. An example of that, I'll show you with the wave here. Let's say we have this wave, and we're going to add it with this wave, which has the opposite phase. If we add those up, they're going to cancel each other out. There's no more wave. They've destructively interfered. Now, if you have a very sophisticated understanding of quantum mechanics, you might say, hey, these are not s orbitals. The 1s orbital doesn't have a node. Yes, I know. They're just examples, and I like to show examples where there's both phases of the wave. So they're just examples of what it means to add orbitals in phase and out of phase. The regions of the orbitals that we're bringing together and overlapping, they will cancel out. And that results in a new orbital that looks like this. So it looks like the orbitals are leaning away from each other. They're not, okay? That's just what it looks like. Really here in the middle, they've canceled out. And because they've canceled out, there is a node here. What are these orbitals called? Well, the orbital that results from constructive interference, we know what that's called already. That's called a sigma orbital. There is cylindrical electron density around the bond axis. What is this other weird orbital called? We have the new node. Well, it also has cylindrical electron density around the bond axis, so it is also sigma. Sigma just refers to the symmetry. However, it's not the same as this orbital for sure. And it is actually what's called an antibonding orbital. It has a node between the two nuclei, and so it's called a sigma star. The star represents antibonding orbital. There's a node between the nuclei. We can draw now a molecular orbital diagram or a molecular orbital energy diagram that shows the orbitals that we started with and then the new orbitals that are formed. So we're imagining that we're taking the 1s orbitals for these hydrogen atoms. So these are the atomic orbitals, A.O, atomic orbitals. We're going to bring them together, and then in the middle of the diagram, we're going to draw the new orbitals, the MOs. So the MOs, molecular orbitals, will be in the middle. I'll write the legend at the top. When the two atomic orbitals overlap constructively in space to make the sigma molecular orbital, that orbital is lower energy than the atomic orbitals. So here it is. There's our sigma orbital. When the two 1s orbitals overlap out of phase, resulting in the sigma star orbital, that orbital is higher energy. Hey, there's a node now between the nuclei, and we said more nodes, higher energy. So the molecular orbitals result, one of them is lower energy, one of them is higher energy, and what you will see is the difference in energy between the atomic orbitals and the antibonding orbital, and the atomic orbitals and the bonding orbital are about the same. They're not exactly the same. I'm not going to go into the details, but they're about the same. The bonding molecular orbital is lower energy than the atomic orbitals. The antibonding orbital is higher energy than the starting atomic orbitals. Now, where do the electrons go? Well, each of those hydrogen atoms has one electron. When they combine, they're each going to go to the bonding orbital. And that explains why the hydrogen molecule exists, right? The electrons are stabilized. They're lower energy in this bonding orbital. Excellent. Electrons and the universe like low energy. Before we leave this slide, I would like to make one more point. Bonding molecular orbitals, such as the sigma orbital in molecular hydrogen, are usually filled with electrons. We can rationalize this based on the low energy nature of the sigma orbital compared to the atomic orbitals in which the electrons started. On the other hand, antibonding orbitals, such as the sigma star orbital in molecular hydrogen, are usually empty. They are unfilled. There is no electrons in these orbitals. That also makes sense, as antibonding orbitals are high energy. They are much higher energy than the orbitals in which the electrons started. So that makes them unfavorable. I would like to stress the use of the word usually in these statements. This is usually the case. Usually bonding orbitals are filled and antibonding orbitals are empty. However, this is not always the case, as you will see as we progress this semester. This is a very important slide. If you have to listen to the explanations again, please do so. Once you feel oriented, move on. Let's get back to the question I asked you a few moments ago, which is, why doesn't molecular helium exist? We can use molecular orbital theory to explain why Molecular hydrogen exists, but helium does not. And then I want you to recall bond order. So if you'd like to pause and define that term, that's fine with me. Both hydrogen and helium would be formed by the 1s orbitals coming together to make a sigma bond. This is how we could describe these bonding interactions with valence bond theory. In the case of helium, I suppose we should propose a double bond. I know that's making you really uncomfortable, so I'll put a little X there. It doesn't happen. Let's explain why. In both scenarios, the atoms will use their 1s atomic orbitals to make the molecular orbitals. When 1s orbitals combine, they generate sigma orbitals, like we've shown, and a sigma star molecular orbital. That happens when two s orbitals are combined, period. So those orbitals are formed. Now we need to think about what happens to the electrons. For hydrogen, each of the atoms has one electron in its 1s orbital. Those two total electrons will populate the sigma molecular orbital. Electrons go to the lowest energy place unless there's some energy applied to make them do otherwise. In the case of helium, each of the atoms has two valence electrons. Just as with hydrogen, two electrons will go to the sigma orbital. However, there are two more electrons and they have to go to the sigma star orbital. That is the next available orbital. For the hydrogen molecule, we can see that overall, for H2, overall, the electrons are stabilized. They've gone to the lower energy sigma orbital. For helium, molecular helium, and our thought exercise here, there is no net stabilization of electrons. Now, it's true that these electrons are stabilized, but the electrons in the antibonding orbital, they're higher energy. They are destabilized, and that cancels out the effect of stabilizing the electrons that are in the sigma orbital. If you looked up bond order, you have remembered that bond order is 1/2 the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. Bond order is a way that we can predict the single, double, triple bond character of a bonding interaction using molecular orbital theory. In general chemistry, I hope you were lucky enough to even use molecular orbital theory to explain things like 1.5 bonds between atoms. Really fun. So for the hydrogen molecule, we can calculate the bond order, which I'll abbreviate BO. 1/2 of the number of electrons in bonding orbitals, those would be the 2 electrons in the sigma orbital, so 2, minus the number of electrons in the antibonding orbitals. Well, the antibonding orbital sigma star is empty, so 0. 1/2 of 2 minus 0 is 1. That is consistent with our prediction of a single bond being formed between the two hydrogen atoms. However, for helium molecule, the bond order again would be 1/2 the number of electrons in bonding orbitals. Those would be 2 electrons that occupy the sigma bonding orbital minus the number of electrons in antibonding orbitals. There they are. There are 2 electrons in sigma star, 2 electrons in the antibonding orbital. Well, 1/2 of 2 minus 2, 1/2 of 0 is 0. Thus, there is no net bonding interaction between the 2 atoms of helium, and molecular helium, as a consequence, does not exist. There's no net stabilization of electrons. Electrons in the sigma orbital are lower energy, but the electrons in the sigma star are not. They're higher energy, and that cancels out the stabilization of the electrons in the bonding orbital. That was fun, but I bet you have some questions. So let's pause. Seriously, let's pause. This is an incredibly important topic, and it can sometimes be an incredibly difficult topic to grasp. It's very important that you take a moment to think about what you know, what you don't know, and what questions you have. So please write down your questions. I will share with you now some of the common questions that I encounter when teaching this topic face-to-face. First, why do both bonding and antibonding molecular orbitals form from the combination of atomic orbitals? So why? Second, what is an antibonding orbital? And third, why do antibonding orbitals matter? / why are we learning this? You told me that antibonding orbitals are usually empty. So if that's the case, why do I care? Did you have any of those questions? Did you have other questions? Let's see if I can answer these 3 questions, and if you had other questions, you should certainly send them to me. First, why do both bonding and antibonding molecular orbitals form from the combination of atomic orbitals? Recall that our models for orbitals are wave functions. The electron is described as both a wave and a particle in quantum mechanics. And waves can either have a positive phase or a negative phase. And I'm showing that phase changing across a node. Nodes, of course, being regions of space where there is 0 probability of the electron existing. Because the wave functions can have either positive or negative phase, that means there are 2 possibilities when the 2 orbitals are combined. The 2 orbitals may have this same phase. Their phases may be aligned. This is like adding up 2 equations. In that case, they will constructively interfere, and you get a new wave. But because an orbital can have 2 phases, it's also possible that when you add up 2 orbitals, they'll be in different phases. That would be like subtracting 2 equations. In this scenario, the 2 waves cancel out. There is destructive interference. The bonding orbital results from the 2 orbitals having the same phase when they combine, resulting in constructive interference. The antibonding orbital results from the 2 orbitals combining in different phases. And now, in this case, you won't have total destructive interference. We only observe destructive interference where the 2 orbitals overlap. So here I'm pretending I'm just completely overlapping the 2 waves in my thought exercise. That's fine, but when the waves are on atoms, you cannot completely overlap them because you're not going to put 2 nuclei on each other. All right, we're just bringing them together in space. So we only observe destructive interference where the 2 orbitals are overlapped. For example, I'll draw a picture at the top of the page. If these are the 2 orbitals, they're coming together. Let's say just these regions of the orbitals overlap, so just those orange regions overlap, because again, there's nuclei in there, and they are certainly not going to overlap. So we're only getting them as close as the bond length, which is different than this picture I drew down here. Those regions that overlap destructively interfere, and that's why we see them sort of cancel out in between the 2 nuclei where they had overlapped. This node results from where the 2 orbitals have canceled out. So here's where they canceled out. There's the destructive interference. I hope it helps to think about this question in this way. Second question, what is an antibonding orbital? The most straightforward way to think about antibonding orbitals is by considering the effect of the electrons on the nuclei. Let's think about an electron in a bonding orbital and an electron in an antibonding orbital and compare those two possibilities. In each scenario, where is the electron most likely to be? For an electron in a bonding orbital, we will consider the example of the sigma orbital made from combining two s orbitals. The electron is most likely to be in between the two nuclei. Let's consider the electrostatic effects of having the electrons between the two nuclei. The electron will attract each of the nuclei towards it. Well, that sounds just like the definition of a bond. Two atoms held together by shared electrons. So the effect of an electron in a bonding orbital is to pull the atoms together. On the contrary, if we consider the sigma star orbital as an example of an antibonding orbital and ask ourselves, where is the electron most likely to be? The electron is most likely to be on the outside of the bond. So not in between the nuclei, but on the outside. After all, there's a node in between the nuclei for this orbital. And nodes are regions of zero electron density. We can draw out the nuclei and an electron. Again, this time the electron is most likely to be outside of the bond for this orbital since there's a node between the nuclei. What effect does this electron have on the nuclei? Well, it's strongly attracting this nucleus. It's weakly attracting the other nucleus since it's farther away. But what else do we have happening here? We have quite a bit of repulsion since there's no electron in between these two positively charged nuclei anymore. So for an electron in an antibonding orbital, there's unequal attractive forces between the electron and the nuclei. You can imagine these attractive forces, like this nucleus is running towards the electron, this nucleus is walking towards the electron. Well, eventually, these two nuclei are going to be really far away from one another, right? So that's the opposite of a bond. That is an antibond. The easiest way for me to think about what an antibonding orbital is just to think about the effect of an electron on the nuclei in each of these orbitals. In a bonding orbital, the electron pulls the nuclei together. They're both attracted toward it, and it's in between them, so it pulls them together. And in an antibonding orbital, the electron is more likely to be on the outside of the bond. So one nucleus is pretty strongly attracted to it, and the other one is not as strongly attracted to it since it's farther away. And that serves to pull the nuclei apart, which is the opposite of a bond, hence an antibonding orbital. Now, yes, this is an oversimplification, but I think when you think about it this way, it starts to make a little more sense about what in the world an antibonding orbital is. Let's move on to our third question. Why do antibonding orbitals matter? Why are we learning this? Wonderful question. Well, why would you think antibonding orbitals don't matter? Yeah, I said that they're usually empty. True, I did. However, they can be filled with electrons. And when they are filled with electrons, then exciting things happen. What sorts of exciting things do you think might happen if an antibonding orbital is filled with electrons? Well, what happened for helium? When we first were thinking about molecular helium and we put electrons in the bonding orbital, maybe we were thinking, yeah, we're going to make a bond. But then we put them in the antibonding orbital, and no, that cancels it out. So there was no bond. Yeah, so one example of exciting things that could happen is that filling an antibonding orbital with electrons can break a bond. Eventually, we'll start to talk about the chemical reactivity of organic compounds. And in many cases, we will use molecular orbital theory to rationalize what's going on. So they matter, accept it for now, and you will see the excitement as we continue on in the class. We have practiced forming sigma bonds from s orbitals, but fortunately or unfortunately, we're not going to be discussing the hydrogen molecule very much in this class. We will, however, be discussing molecules based in carbon, right? And lots of them. So let's construct a molecular orbital diagram for the CH sigma bond in methane. It may help to draw methane. We should consider what orbitals are used to make that sigma bond. Yes, it's the 1s on hydrogen and the sp3 orbital on carbon. That carbon is sp3 hybridized. There are 4 electron domains and tetrahedral geometry. That corresponds to sp3 hybridization. When the carbon sp3 orbital comes together with the 1s orbital for hydrogen, and no, these are not drawn to scale, there are 2 possibilities. The orbitals could combine in phase. Where they will overlap, there will be constructive interference. They will add up between the 2 nuclei. And a sigma orbital, a sigma bonding orbital, will be observed. There's the carbon, there's the hydrogen. However, when 2 orbitals are combined, 2 orbitals must result. As we have discussed, the second possibility is that the 2 orbitals, when they come together out of phase. Where those 2 orbitals overlap between the 2 nuclei, destructive interference will occur. They will cancel each other out. Sigma star CH will result. This orbital has a node between the 2 nuclei. I understand that it looks like the big lobe and the little lobe of the sp3 orbital just swap places. That's not what happened. The big lobe of the sp3 orbital, it actually was canceled out where it overlapped with the 1s orbital of hydrogen out of phase. So there's a node between these 2 nuclei. Sigma star is an antibonding orbital. So from the combination of these 2 atomic orbitals, 2 new orbitals are formed. A lower energy sigma CH, a bonding orbital, and a higher energy sigma star CH, an antibonding orbital. We have now drawn the cartoon molecular orbitals that describe the bonding interaction between carbon and hydrogen. If I ever would like you to do this, I will refer to this exercise as drawing the cartoon molecular orbitals. Now let's draw the energy diagram. We'll do it beside the cartoon molecular orbitals. So I'm going to move methane out of the way here. So now I'm drawing an energy diagram. So there's the sigma CH low energy orbital. There's the sigma star CH, a higher energy orbital. How many electrons are in that CH bond that we're considering here? 2. Where do they go? Yes, the lower energy orbital, the bonding orbital, sigma. As we would expect, the bonding orbital is filled and the antibonding orbital is empty. What would a complete molecular orbital diagram look like for methane? A complete molecular orbital diagram will look like this. It's an energy diagram. You don't have to draw pictures of the orbitals. You just have to name them, show their relative energies, and put the electrons in the appropriate orbitals. Complete molecular orbital diagrams include all bonds and lone pairs. To do this, you would first figure out the number and types of bonds. Then you would rank the orbitals in terms of energy. Sigma is lower than atomic orbitals, so bonding orbital is lower energy than atomic orbitals, which are lower energy than sigma star antibonding orbitals. And finally, you would put the electrons in the lowest energy orbitals. Now you know how many electrons there should be, because you can all draw Lewis structures and you can all understand Lewis structures, so you can count electrons. So make sure you know how many electrons there are and that they're in the lowest energy orbitals. And again, those lowest energy orbitals, they're going to be the sigma orbitals, the bonding orbitals, and if there are lone pairs, atomic orbitals. We do expect antibonding orbitals to be empty. So for methane, you can pause and try this yourself if you like, or you can do it along with me. We see that there are 1, 2, 3, 4 sigma CH bonds, meaning there are 4 sigma CH orbitals. If there are 4 sigma CH orbitals, there are also 4 sigma star CH orbitals. There are no lone pairs, so we don't need to worry about that. We will arbitrarily call this point on the diagram 0. This is 0 energy. That would be the energy of an atomic orbital. These are all relative energies anyway, so we'll call that our 0 point, the energy of an atomic orbital. Lower energy are the sigma CH, the bonding orbitals. About the same difference in energy above the 0 point will lie the antibonding orbitals, sigma star CH. How many electrons should we put in these orbitals? Well, there are 2, 4, 6, 8. Those 8 electrons will go into the lowest energy orbitals. Bonding orbitals, the low energy orbitals are filled. The high energy antibonding orbitals are unfilled, just as we would expect. Be sure that you feel oriented and understand this exercise. Watch it again if necessary, because we are going to try again now, and you should try yourself first to draw an MO diagram for the carbon-carbon sigma bond this time in ethane. And then, once you've done that, draw a complete molecular orbital diagram for ethane, for all the bonds in ethane. Pause and give that a try. Now let's compare our answers. So the sigma bond in ethane is from a carbon sp3 orbital. So we can number our carbons if we want, carbon 1 and 2. So from a sp3 orbital on carbon 1 and an sp3 orbital on carbon 2. How do I know that? Well, both of these atoms are sp3 hybridized. They have tetrahedral electron pair geometry. Atoms that are sp3 hybridized only have sp3 orbitals. They have 4 sp3 orbitals with which they make their bonds or hold lone pairs. There are 2 possibilities when these sp3 orbitals come together in space to make a bond. They can add in phase, resulting in constructive interference between the nuclei, and a sigma CC orbital, a bonding lower energy orbital. However, these 2 orbitals could also add out of phase. Why? Well, because each of them can exist in either phase. They can exist with the big lobe with a negative phase or the big lobe with positive phase. Both of those possibilities exist, and so that means when they combine, both of these possibilities occur. This is what it would look like for 2 carbon sp3 orbitals to add out of phase. You can see their big lobes have different phases, and where the big lobes overlap, we will this time see destructive interference, whereas when they added in phase, we saw constructive interference. And we saw them add up between the 2 nuclei. Now they're going to cancel out between the 2 nuclei, and the resulting orbital will look like this. There is now a node between the 2 nuclei. The biggest regions of electron density for this sigma star CC orbital are on the outside of the bond axis, just as we said a few slides ago. So this is an antibonding orbital. It serves to pull the nuclei apart when it is populated with electrons, which usually it is not. So combining the 2 sp3 orbitals in phase or out of phase resulted in a lower energy bonding orbital, or when combined out of phase, a higher energy antibonding orbital. Now that we've drawn the cartoon molecular orbitals, let's put electrons in them and draw an energy diagram. Sigma Cc, the bonding orbital, is lower energy than the starting atomic orbitals. Sigma star Cc is higher energy than the starting atomic orbitals. There are 2 electrons in this bond. Where will they go? Yes, to the lowest energy orbital, which is sigma Cc. Now that we have that down, let's draw a complete molecular orbital diagram for ethane. Recall the steps that we discussed for the previous example. You should determine the number and types of bonds and lone pairs. You should list those orbitals and lone pairs. For every bonding orbital, there's an antibonding orbital. Once you've made that list, then you can rank the orbitals in terms of energy, and then put them on the diagram, fill in the orbitals with electrons. Give it a shot for ethane. Last chance to fill in this diagram before we discuss our answers. There's one sigma Cc bond, so there's one sigma Cc orbital and one sigma star Cc. There are 6 sigma CH bonds, so there's 6 sigma CH orbitals and 6 sigma star CH orbitals. Now, a question that you might have, what are the relative energies of the sigma CH and sigma Cc orbitals? Because we know they're both going to be lower than the atomic orbitals, but do they have the same energy? Do they have different energies? Well, these 2 types of orbitals have roughly the same energy, but I want you to use the rule of thumb that orbitals of the same type, so sigma orbitals, from more electronegative atoms are lower energy. Carbon and hydrogen have pretty similar electronegativities, so sigma Cc is just slightly lower energy than sigma Ch. We see the same phenomenon for the sigma star orbitals. Sigma star Cc is just slightly lower energy than sigma star Ch. Now, to fill in electrons, there are 14 electrons in ethane. So we need to fill those in the lowest energy orbitals. So 2, 4, 6, 8, 10, 12, 14. And then we stop and check. What should we check? Yeah, you might want to check that your total electrons equals the total electrons that you would count using group number on the periodic table, because that should be consistent with your Lewis structure as well. You want to check that bonding orbitals are filled and antibonding orbitals are empty. Again, that will not always be the case, but it will usually be the case. Take a moment, make sure, again, just like with the previous exercise, that you've got this down. The new elements for this example are that we looked at a CC bond instead of a CH bond, and then we had to decide the relative energies of orbitals of the same type, such as the sigma orbitals, but when they're made from different atoms, so sigma CH versus sigma CC. And we're going to use electronegativity to decide which orbitals are lower energy. All right, reflect, listen again, and then it's time to move on, and we're going to make some pi bonds. We are now ready to form pi bonds from leftover p orbitals. I will remind you that what is meant by leftover p orbitals are those not used to make hybrid orbitals. Begin by pausing, drawing the Lewis structure for ethene, C2H4, and then describe all of the bonding interactions in ethene. What is meant by describe the bonding interactions is simply what we did here. Sigma from C1sp3 and C2sp3, for example. It is also what you did at the end of the valence bond theory lesson. And I believe you've even already done this for ethane. Please pause. Each of the carbons in ethene has 3 electron pair domains around it. Thus, they have trigonal planar electron geometry and are sp2 hybrids. Recall that we imagine that sp2 hybridization occurs by combination of the s orbital and 2 of the p orbitals to form 3 new hybrid orbitals. These 3 hybrid orbitals are all located in the same plane at a 120-degree bond angle for one another. sp2 hybridization explains observed trigonal planar geometry. There was one p orbital that was not combined to make the hybrid orbitals, and it's this p orbital that I refer to as left over. It is at a 90-degree angle to the hybrid orbitals. Let's now describe the bonding interactions in ethene. Each sigma CH bond is formed from the combination of a 1s orbital on hydrogen and an sp2 hybrid orbital on carbon. Hybrid orbitals make bonds and hold lone pairs. The carbon-carbon bonding interaction is a double bond. There is a sigma CC bond between sp2 orbitals on both carbons. Yes, hybrid orbitals make sigma bonds and hold lone pairs. And then there is a pi interaction between the leftover p orbitals on each of these carbons. P orbitals make pi bonds. We can draw out the bonding picture if we would like, and I would like. And I'm going to try to do this in a little bit different of an orientation. I'm going to imagine that we take ethene and we rotate it in space. So we're going to rotate it so that the carbon-hydrogen bonds are coming in and out of the plane of the board, or in this case, the plane of your computer screen, like that. I will ignore the little lobe of the sp2 orbitals. So now this one is coming out of the plane, making a bond to hydrogen. So here we've shown the 3 sigma bonds that can be made from the overlap of the hybrid orbitals. Then there's that leftover p orbital. It will make the pi bond. Let's show that. So when I draw the sigma bonds in this orientation coming in and out of the plane of the paper, the p orbital is in the plane of the paper. It is at a 90-degree angle to the sigma bonds to the hybrid orbitals. Okay, and then when the p orbitals come together, they make the pi bond, they combine in phase. So we have our pi interaction. This was the picture that we developed together when we discussed valence bond theory. Of course, when this pi interaction is formed, when those 2 p orbitals combine, there are 2 possibilities, right? They combine in phase and out of phase. So let's go through that now. When the orbitals come together in phase, where they overlap, there is constructive interference, forming a pi orbital. Pi orbitals have electron density above and below the bond axis, but a node on the bond axis. That node on the bond axis comes from the node in p orbitals. That is at a 90-degree angle from the orbital axis. This makes it a pi orbital. So both pi and pi star have that node, again, which comes from just the nodal plane in p orbitals. But because the p orbitals can either have phasing like this, or they can have phasing like this, both combinations, in phase and being added out of phase, are possible. When the 2 p orbitals come together out of phase, they cancel out. They destructively interfere between the 2 nuclei. And so this new node is formed where the 2 wave functions have canceled each other out. Pi star can be represented in either of these formats. So you know that the orbital pictures look like these, but chemists, it's kind of hard to draw these 2 pictures, right? So we can communicate effectively pi and pi star by lining up 2 p orbitals in phase or out of phase. And that is totally fine. These pictures here, they're easier to draw and totally acceptable. The pi star orbital is an antibonding orbital. due to that node between the two nuclei. Now that we've drawn the cartoon molecular orbitals that describe the molecular orbitals formed from the combination of two p orbitals, right? You combine two orbitals, you get two orbitals. We can draw now the energy diagram that describes their relative energies. So here's our zero energy. This would be the energy of a p orbital. The pi orbital is lower energy. The pi star, the antibonding orbital, is higher energy. There are two electrons in the pi orbital. So there are two pi electrons in this carbon-carbon bond. We're not thinking about the sigma electrons. And so those two electrons go here to that pi orbital. Let's now draw a complete molecular orbital diagram for all of the bonds in ethane. And I'll actually ask that you pause and do this yourself and then come back and check with me. The first step is to list all of the orbitals that will be found for the molecule you're analyzing. There are 4 sigma CH bonds. That tells me there are 4 sigma CH orbitals and 4 sigma star CH orbitals. For the carbon-carbon bonding interaction, there is 1 sigma bond, which means there is 1 sigma CC. If there's a sigma CC, there is also a sigma star CC. An antibonding orbital is formed when a bonding orbital is formed. The other bonding interaction in this double bond between the two carbons of ethane is a pi interaction, and we've just analyzed it here. A pi CC orbital and a pi star CC orbital are formed from this pi bonding interaction between those two carbons. Now, relative energies. Well, we know that the bonding orbitals are lower energy and the anti-bonding orbitals are higher energy. And we know that sigma CC will be just ever so slightly lower energy than sigma CH because carbon is ever so slightly more electronegative than hydrogen. And that is how I've asked you to evaluate the relative energies of orbitals of the same type, such as sigma, made from different atoms, such as hydrogen versus carbon. The only thing we may not remember is the relative energy of sigma versus pi orbitals. Do you remember what is lower energy, a sigma orbital or a pi orbital? Well, sigma orbitals have cylindrical electron density around the bond axis. Pi orbitals have electron density above the bond axis and below the bond axis. And what is on the bond axis? Yes, the nuclei. Thus, sigma bonding interactions are lower energy than pi bonding interactions. So sigma orbitals are lower energy than pi orbitals. Let's put all of this together. The lowest energy orbitals for ethane are the sigma orbitals. We have the 4 sigma CH orbitals and the 1 sigma CC. Let's just cross those off our list. Next, we have the pi CC orbital. Cross that off our list. Where do the antibonding orbitals fit in? Well, they fit in above the energy of the starting atomic orbitals, which I've indicated here. Now, when the bonding and antibonding orbitals are formed, when the molecular orbitals are formed, remember, so I'm going to refer to this diagram here. Remember that the bonding orbital is lowered in energy about the same amount as the antibonding orbital is raised or is higher in energy than the starting atomic orbitals. So the next orbital that we should put into our diagram is pi star CC. And then finally, we have our sigma star orbitals. We will have the 4 sigma star CH orbitals, and then slightly lower energy is the sigma star CC. So this symmetry that you see between sigma is the lowest energy, then pi star, then sigma star. This results from the fact that antibonding orbitals are raised in energy, the same amount as bonding orbitals are lowered in energy. We see that for both the orbitals of pi symmetry and of sigma symmetry. And I'll say that in a different way, but one more time. So pi cc, pi orbitals, are a little higher energy than sigma orbitals, but pi star orbitals are a little lower energy than sigma star orbitals. And there will be important consequences to that as we move forward in our course. Let's put in the electrons. There are 12, 2, 4, 6, 8, 10, 12 electrons in ethene. Put them in the lowest energy orbitals first. So that's 10, and here's 12. And then you check that the bonding orbitals are filled and the antibonding orbitals are empty. When I was explaining the relative energies of these orbitals, I said a lot, and it's not all written down. So you might want to listen to that part again. When you feel ready, let's move on. Summarize what you've learned from the previous examples by responding to this question. What can we say about the relative energy levels of the molecular orbitals that we've encountered? Write down your answer and then check with me. The lowest energy orbitals are the sigma bonding orbitals, then pi, then non-bonding. Quick note, I've been calling the non-bonding orbitals atomic orbitals. I'm going to switch to saying non-bonding now because when we look at, say, the lone pairs of chlorine in this molecule, I would like for you to refer to these as non-bonding electrons. As it turns out, technically, even non-bonding electrons, even lone pairs, are in molecular orbitals, and they have roughly the same energy as the starting atomic orbitals in our approximation. So I don't want you to get confused, but I'm going to transition to using the term non-bonding instead of atomic orbitals when I set the 0 point, the middle point of our energy diagram. Higher energy than non-bonding or atomic orbitals are pi star, and then the highest energy is sigma star orbitals. Now, within each group, okay, so I'm not going to write this out for every group, but within each of these groups, so within sigma, for example, orbitals made from more electronegative atoms will be lower energy. I can give you a quick example of that, actually. Let me change this molecule on the left. I'm going to change it to chloroethane. And then we can think about sigma bonds for a minute. So we have two sigma bonds. Well, we have a bunch of sigma bonds. We have sigma CH, and we have sigma CC, and we have sigma CL. So let's write that out. The lowest energy orbital among these 7 is the sigma CCl orbital because chlorine is more electronegative than any of the other atoms that are bonding with carbon. Then there is sigma CC. Then we would have the 5 sigma CH. Now, again, sigma CH and sigma CC really, really close in energy. But we put sigma CC just a little bit lower since it's a little more electronegative than hydrogens. I'm comparing the atoms that are bonding to carbon, right? Each of these orbitals has that first carbon in common, and then the carbon is bonding to a different atom with different electronegativities. And we could repeat the same order in sigma star. If there is one sigma CCl, there's also one sigma star CCl, and that would have the lowest energy of all the sigma star orbitals in this molecule. Then we'd have the sigma star CC, then the sigma star CHs. All right, I hope that helps. So these two trends need to be committed to memory. So the relative energies of the types, the symmetries, the types of orbitals, and this caveat that within each group, orbitals made from more electronegative atoms are typically lower energy. So we need to commit those two things to memory and apply them to problems. Speaking of problems, let's draw a complete molecular orbital diagram for all of the bonds in ethyne. You don't need to draw the cartoon molecular orbitals. You just need to draw the energy diagram. If you don't feel ready to try this on your own right now, then you might take a break, but you should definitely try it on your own before you listen to me explain it. Make sure you understand what we've been talking about for the past however long it's been. I've drawn the valence bond description of acetylene at the top of the page, and I hope that helps. It's a place for you to start and review before we draw the molecular orbital diagram. To draw the molecular orbital diagram, you should follow the steps that I've written out on this side of the page. You should list the orbitals given the Lewis structure. Well, we've done that. We've practiced that, at least for the bonding orbitals in the valence theory description, the valence bond theory description. So there are 2 sigma CH bonds. Thus, there are 2 sigma CH orbitals. All bonding orbitals have an antibonding orbital, right? When 2 orbitals are combined, 2 are formed, and an antibonding sigma star CH is formed for each of those bonding sigma CH interactions. Don't forget non-bonding. While there are no lone pairs, no non-bonding electrons for this molecule, so we don't have to worry about that, but in the next example we will. Next, we have the CC bonding interaction. There's the 1 sigma CC and also a sigma star CC. Then 2 pi interactions, so 2 pi CC orbitals and 2 pi star CCs. Now, don't forget non-bonding electrons is the next tip I've given you here. There are no lone pairs, there are no non-bonding electrons for this example, but in the next example, we will need to apply this tip. Number 2, rank orbitals in terms of energies. Remember, sigma is lower energy than pi, is lower energy than non-bonding, is lower energy than pi star, is lower energy than sigma star. So, and then within each group, orbitals form from more electronegative atoms or lower energy. Let's start with our sigma orbitals. So 2 sigma CH orbitals, and we need our sigma CC. That'll be slightly lower energy than the sigma CH. Next, pi. We have the pi CC orbital, and there's 2 of them, and they will have equal energies. They'll be degenerate. There's no difference between the 2 pi bonds here. They're both made from p orbitals from the same carbon atom, so they have the same exact energy. Next, pi star CC. If we'd like, we can throw on that 0 point. This will be the energy of the non-bonding or atomic orbitals. And then finally, our highest energy orbitals are the sigma star orbitals. So 2 sigma star CHs and then 1 sigma star CC orbital. Step 3, put electrons into the lowest energy orbitals. If we look at acetylene at the top of the slide, we see there are 2, 4, 6, 8, 10 valence electrons. We could also get that from the formula. There's 2 carbons, so there's 4 valence electrons from each of those for 8. There's 2 hydrogens, 1 valence electrons from each of those, so 2. So that gives us 10 total electrons, 10 total valence electrons in the molecular orbitals. Putting those electrons in the lowest energy orbitals results in a diagram that looks like this. Now we need to check these 3 things. So be sure that the bonding orbitals are filled, the antibonding orbitals are empty. Don't forget non-bonding. Well, there are no non-bonding for this molecule, so we can skip that. And then check your total valence electron count. So there should be 10 valence electrons. We have 10 in the diagram, so we're good to go. Let's try another example once you've reviewed this and you feel comfortable with it. This time we'll draw a complete molecular orbital diagram for all of the bonds in acetonitrile. If you'd like, pause and draw the structure of acetonitrile. I'm about to draw it for you. Here is the structure of acetonitrile and our steps for writing a complete molecular orbital diagram. Please, for sure now, even if you didn't pause before, pause and try this exercise. We'll begin by listing all of the orbitals involved in bonding for acetonitrile. There are 1, 2, 3 sigma CH bonds. That means that there are 3 sigma CH orbitals and 3 sigma star CH orbitals. For every bonding orbital, there is an antibonding orbital. There is one sigma CC bond. Thus, there is one sigma CC orbital and one sigma star CC orbital. We will now move to the triple bond of acetonitrile. The first bonding interaction that we will consider is a sigma bonding interaction. So there is one sigma CN orbital and one sigma star CN orbital formed when the sp orbitals of carbon and nitrogen come together to make that bond. Just like when we examined ethane, when the two carbon atoms came together, they could add in phase or out of phase to make both a sigma CC and a sigma star CC. The same thing happens for carbon and nitrogen in acetonitrile when they use their sp orbitals to bond. The remaining two bonding interactions between carbon and nitrogen are pi interactions, and there are two of them. So there will be two pi CN orbitals and two pi star CN orbitals. Let's not forget the non-bonding pair of electrons drawn on nitrogen. Technically, those two are in a molecular orbital, but let's not worry too much about that. So we have one non-bonding nitrogen. Okay, now there's no antibonding or anything that goes with that, just non-bonding, so that's all we need to write down for that lone pair of electrons. Now that we've listed the orbitals, we can rank them in terms of their energies and put them on our diagram. The lowest energy orbitals are the sigma orbitals. Among that group, the lowest energy orbital will be the sigma Cn. That is because nitrogen is more electronegative than carbon. Then we'll have the sigma Cc, and finally the 3 sigma Ch orbitals. Let's check those off of our list. Next, pi. There are 2 degenerate pi Cn orbitals. Then the non-bonding pair of electrons on nitrogen, the non-bonding orbital. Now pi star, 2 degenerate pi star Cn orbitals. Then the sigma stars. So we have 5 sigma star orbitals. Just as we did for the sigma orbitals, we order them by electronegativity. Orbitals derived from more electronegative atoms are lower energy. So the lowest energy of the sigma star orbitals is the sigma star Cn. Then the sigma star Cc. The highest energy is the sigma star Ch. Now we put electrons into the lowest energy orbitals. There are 2, 4, 6, 8, 10, 12, 14, 16 valence electrons for acetonitrile. Into the lowest energy orbitals they go, and then check to be sure that you've done this correctly. So there are 16 total electrons. We see the bonding orbitals are filled. The lone pair is there. Don't forget the non-bonding. The lone pair is there. And then the anti-bonding orbitals are empty. So this looks good. All right. You're ready to do some practice problems on your own. Before I set you loose to do that, I want to make sure that we understand where this relative energies of orbitals from more electronegative atoms comes from. The starting energies of atomic orbitals affect the energies of the molecular orbitals that are made. You may recall from general chemistry that atomic orbitals from more electronegative atoms are lower energy than the atomic orbitals from less electronegative atoms. As we proceed across row 2 of the periodic table, we can see that the energies of the 2p and 2s orbitals of those atoms decreases. Let's apply this idea to the bonding interactions between, say, 2 carbons in an alkyne and then the carbon and nitrogen in a nitrile, such as what we were examining on the previous slide. When the sigma bonds are made between the two carbons in an alkyne, or the carbon and the nitrogen in a nitrile, they are made from the sp hybrid orbitals that those atoms have. And the sp hybrid orbitals are derived from atomic orbitals, right? So we can conclude that the sp orbital on nitrogen is lower energy than the sp orbitals on carbon. Let's start by considering the sigma orbitals formed from the combination of two sp2 orbitals on carbon. Just like for the ethane example, when those two sp orbitals combine, we'll form two new orbitals, a sigma orbital that is lower energy than the atomic orbitals, and a sigma star antibonding orbital that is higher energy than the starting atomic orbitals. The sigma orbital is lowered in energy about the same amount that the sigma star orbital is raised in energy. When the sp orbitals for carbon and nitrogen combine to make the sigma interaction in, say, a nitrile, so just thinking about the sigma interaction for this comparison, the resulting orbitals will be a sigma, a bonding orbital, and an antibonding orbital. Just as for the CC interaction, the bonding orbital is lower energy than the atomic orbitals, and the antibonding orbital is higher energy than the atomic orbitals. If we think about the midpoint here between the energies of the two orbitals, this sp on carbon and the sp on nitrogen, the bonding orbital is lower energy, about the same amount as the antibonding orbital is higher energy. Now, what do you notice here? A couple of things. We notice that the sigma Cn, the bonding orbital made when the more electronegative nitrogen atom bonds with carbon rather than another carbon atom bonding with carbon, right? So we're comparing nitrogen bonding with carbon versus carbon bonding with carbon. That sigma orbital is lower energy than the sigma Cc because it started out lower energy due to being made from the more electronegative nitrogen, which has lower energy atomic orbitals. Same idea for the antibonding orbital. Check it out. The antibonding orbital, sigma star Cn, is lower energy than sigma star Cc because it too started out at a lower energy due to the lower energy orbitals of the more electronegative nitrogen. If you were wondering why orbitals from more electronegative atoms are lower energy, now you know. If it totally blew your mind, let it float away like a cloud and just memorize it. Hate to say that, but it's okay. We have a lot going on. Before we finish today, I would like to introduce frontier molecular orbitals because it is often useful in chemistry to identify the highest energy occupied molecular orbital, aka the HOMO. Occupied means filled with electrons. And the lowest energy unoccupied molecular orbital, aka the LUMO. Unoccupied means no electrons, because these two orbitals are involved in chemical reactivity. So being able to identify them is quite useful for us. Before we go back and identify the HOMO and LUMOs for the previous examples, let's just think about what types of orbitals might be HOMOs and LUMOs in general. Which of these orbitals are typically filled? Yes, definitely the sigma and pi bonding orbitals, otherwise there wouldn't be a bond. And then often the non-bonding are filled as well. So we saw in the previous example for acetylene, we saw this non-bonding pair of electrons, so that represented a filled orbital. However, we will see some examples where non-bonding orbitals are empty. So when we encounter carbocations, this has a non-bonding p orbital that is empty. That's why it has a positive formal charge. So non-bonding orbitals could also be empty. And these are just two examples of non-bonding filled with electrons and non-bonding unfilled, empty. So these are our possible unfilled, empty orbitals. So the highest energy filled orbital, So non-bonding, pi maybe. Those will be of interest to us. And the lowest energy empty orbital. So pi star, non-bonding usually. Let's go back to the previous examples now and identify the HOMOs and LUMOs for each of these molecules. And then I think you'll see why they're called frontier molecular orbitals. So for acetonitrile, let's look for the highest energy filled orbital. Which one is it? Yeah, the highest energy filled orbital is the non-bonding pair of electrons on nitrogen. So this is the HOMO for acetonitrile. The lowest energy unfilled orbital is, yeah, we have two of them. They tie. Pi star Cn. So that's the LUMO for acetonitrile. And so maybe now you see why they're called frontier molecular orbitals. They're on the edges. So the LUMO is the lowest energy. It's on the edge of the antibonding and the empty orbitals. And the HOMO is on the edge, the end of the bonding orbitals. So frontier molecular orbitals. Whether or not you get the name, just make sure you can identify HOMO and LUMO. Highest energy occupied, filled with electrons orbital, and lowest energy is going up, right? Empty, unoccupied molecular orbitals. Let's try now for acetylene. What are the HOMOs and LUMOs for acetylene? Pause and try this yourself. Right, the highest energy filled molecular orbital, it's a tie because these are two degenerate pi cc orbitals. And the LUMO is also a tie between the two degenerate pi star cc orbitals, which are empty. Awesome. If you'd like to go back to all the other examples we looked at and identify HOMOs and LUMOs for those molecules as well, that is perfectly fine with me. Have fun. But I am going to move on now and ask you, are you still wondering why this is important? Well, if you are, that's fine. You're allowed to wonder, but molecular orbital theory is a predictive model, and it's an explanatory model. It will help us to explain, to rationalize, and to predict chemical reactivity, which we want to be able to do. If we can make predictions, we don't have to memorize 5 gazillion different things. Before we wrap up, let's take a moment and reflect on our theme for this first unit of our class. Chemistry is all about electrons, and electrons go to the lowest energy orbitals, period, always, unless they are given some energy to do otherwise. Based on what you've learned so far, what are the lowest energy places for an electron? Stop and maybe just write what's new that you learned today. The new information that we learned today, or that we solidified today, is really summarized already on this chart. This chart's really important. The lowest energy bonding orbitals, or the lowest energy molecular orbitals, are sigma. And then within the sigma group, the lowest energy orbitals are made from electronegative atoms. And the example we gave was this carbon-chlorine orbital. Next lowest is pi, so still a bonding orbital, so still lower energy than non-bonding, than the starting atomic orbitals, which is next. And then antibonding orbitals, they are the highest energy types of orbitals, where sigma star is the very highest type of energy antibonding orbital, and a little bit lower was pi star. So this is the new knowledge that you gained today regarding the energies of the places, the orbitals, electrons can occupy. So be sure that you think about this question and write out your list of all the low energy places for an electron to occupy. Summarize the learning goals. Can we draw molecular orbital diagrams for simple, and by simple I do not mean easy. It is not easy. I just mean small molecules that contain few atoms. Yes, you can do it. We did some examples here. Please live, learn, love these steps, and you'll be able to achieve this goal. Next, rank the energies of molecular orbitals. Yeah, you can do that. We've been talking about it. We just talked about it, right? Here we go. Draw sigma and pi molecular orbitals. You can do that too. Sigma orbitals are made from hybrid orbitals, and we had some examples. They have cylindrical electron density along the bond axis. So we looked at the sigma orbitals formed in ethane. We practiced drawing pi orbitals for ethene. So we do the pi orbitals here. Pi orbitals have electron density above and below the bond axis, but not on it. They are formed from p orbitals. Finally, can you explain the difference between a bonding and an antibonding orbital? I believe in you. So try it. And then if you want to check whether or not you did that correctly, there's a few places you can look. So we discussed it here when I was answering questions that you might have. And then we discussed it every time we built a molecular orbital diagram. Antibonding orbitals have nodes between the two nuclei that result from destructive interference, adding two orbitals out of phase. The shaded, the positive, if you like to think about it that way, and the negative phase, they canceled out up here, and that is responsible for this part of the node. The unshaded, the negative phase, and the positive phase, they canceled out down here. That's responsible for this part of the node. So nodes are formed when orbitals are added out of phase, resulting in destructive interference. And I drew for you these simplified waves to think about constructive and destructive interference back at the beginning of the lecture. So that's it. We did it. We achieved our learning goals. But we need to solidify these goals. If you do not practice within 24 to 48 hours, you will lose it all. And then you will have to do it again. And we don't want that. So please practice. It is time to practice. Before you practice, summarize and reflect. Ask me any questions you have. Think about how the organic chemist molecular orbital theory relates to what you learned in general chemistry. Or did you learn it at all in general chemistry? And practice, practice, practice. If you're still listening, you can't tell, I love molecular orbital theory. It's so fun. If you want to talk about it, I'm happy to talk about it anytime.